So our line integral, which is this Vx dx plus Vy plus Vz dz, will, I mean, all this dx, dy and dz will be written down into some terms times d lambda. So, and this Vx, Vy and Vz itself is a function of x, y and z, and x, y, z itself is a function of lambda. So we can just remove this x, y and z and write the function Vx, Vy and z and Vz into the form of lambdas. So finally all of these terms is going to have this lambdas as a function and d lambda as the this integrand, and we will sum all of this thing, and we will left with this number and this lambda, and we're gonna have this one single integration. And how we will deal with this vectors a and b, position vector a and b? Again, position a and b vector is nothing but this coordinate x, y and z at the initial and x, y, z at the final. Okay, at the initial and at the final. And putting writing this x, y, z, putting that into the this x, y and z curve, will get the lambda for a and lambda for b, and plug these values of lambda at the lower limit and the upper limit, we can solve this integration. And in this way we can calculate the line integration of a vector field a, vector field v. Okay, in this way we can solve it. Right. Okay, so let's come back to this line integral. Okay, so we have seen that how we can calculate the line integral by writing the parametric equation of this curve. Okay, or another way, we can actually equation a curve, the equation of a curve can be given by some it can be written, the x would be written by some let's say some maybe some function of y, and again x can be written as some function of z. So the equation of that curve can be written in these two forms. Okay, so I mean these two equations. Okay, so I mean instead of replacing this x with lambda and y with the lambda and z with the lambda, we can just replace leave the x as it is and replace y with the x and z with the x, and in this way all the variables will be written in the form of x, and x can be this integration, line integration, can be solved in the form of x also. Okay, now let's come to the physical significance of this line integral. Okay, so this is the line integral of a vector field a. Okay, in physics, this first of all, in physics, this curve may be a particle, it may be a charged particle, let's say electron is moving in this way, and the trajectory that is drawn by this electron is the curve that we have mentioned over here. Okay, so okay, so we're gonna have this vector field, let's say a. Okay, and by chance if that vector field a is a force vector field, so the line integral f dot dl will represent the work done by a particle that moved through a curve under the force field F. Okay, if it moved from A to B. Right, so a line integral can represent the work done by a particle when it moves through a trajectory, okay, under a force field F, right. Now suppose that that particle will start from a point A and moves all over space and come back to the same point where it started, okay. So in that case we represent this line integral by this symbol, right. This is the closed integral. This closed curve represents that we are starting from a point and come back to the same point, okay. And if that force field is a conservative, then that integral is going to be 0. That means the work done by a particle in a conservative force field will be 0, right. Or in the reverse manner we can say that if the closed line integral of a force field is 0, then that means that this F, the force field F, is conservative. And in the electromagnetism, this electric field is actually a conservative field, but this magnetic field is not conservative, okay. We will see this. Right. In the next video I will start the topic surface integral, okay.